to our Common Lisp video series, our Common Lisp tutorials. In this video we're going to start a new series, I think. We're going to look at object orientation in Common Lisp and have a look at the different features that exist, because Common Lisp has a different, probably more traditional implementation of object orientation than many languages today. And I'm not going to get into what we understand as classes yet. We're going to start from the beginning, I think. And before object orientation as we understand it today was a thing, languages would have simple things, and this is still true today. Languages like C, they don't have classes, they have this idea of something called a struct or a structure. This is sometimes also known as a record type. And in C, it's not really a record type, it's just pointers to blocks in memory, but that's kind of C for you. Anyway, this record type is a little bit more evolved in Common Lisp. Of course, Common Lisp wasn't fully standardized until 1994, but was around in the early 80s as well. So Common Lisp is at a very interesting point where, when it started, it implemented these record types, these structs, but by the time it had been fully standardized, it had a rather complete object-orientated system built into it. And the journey of learning object orientation in Common Lisp may take several videos, so we're going to start at the beginning. We are going to look at structs today. I intended on recording this video yesterday, but I went down a rabbit hole and, well, needless to say, it didn't happen. You can see that I'm recording this at 8:30 on a Friday evening. That's okay. I certainly hope you enjoy what we've got here. Now, a few things to note, and forgive the rustling, I've got my notes and my samples ready. Common Lisp's object system, its classes, use multiple inheritance, which is good. However, its structs are single inheritance. So the structs are a much simpler way to look at code. However, if you find structs frustrating or limiting, please do not take them as indicative of the class-based system that Common Lisp has. There are two very different things, and they have some overlap, certainly when it comes to things like methods, but that's just simply because of the way Common Lisp implements certain things. It's just very interesting, but we won't really get into those today. We're just going to look at structs on their own merit. And creating a struct is very, very simple. Now I believe what we have here, and I'm just going to restart my interpreter from scratch just to make sure I've got nothing lying around there. If I evaluate that, we see in the bottom left hand corner there that we have this this person, and this will create a new type first because of the way types work in Common Lisp. And in addition to defining a new struct here, a lot more has happened behind the scenes than just defining a struct. What's actually happened is Common Lisp has created a constructor, it has created a copy function, and it's created a few things like a predicate function as well. So what we can do So we can see here from what's being evaluated in the bottom left there that we have this make person function that has been created. It takes a keyword called name, which it maps onto the property in the struct there. And in addition to the constructor, the copier, and the predicate, which we'll get to in just a moment, it also creates the reader function. So we have this person name, which has been created for us. This didn't exist previously. And it also enables those readers to be setfable. So if we wanted to, we could also do this. So let's say we want to change the person's name, setf, person name, P, John. So we can see here now again in the bottom left that we have John, even though the make person constructor was called with name Bob. The reader functions are setfable, and so we can change the underlying values in the data structure there. Now we can. I touched on the fact that we have a predicate function. So we get this person P function, and if we pass in a person object, we get T. If we pass in a number, we get nil. So we can determine whether an object is a person or not. And in addition to this, and so, as I mentioned, we get a copy function called copy person, and that allows us to copy a struct, or rather the instance of a struct, and we can create a copy. So fundamentally, in the simplest way of looking at a struct here, we get a constructor, the make person. We get reader functions for all of the properties that we define on that struct, and they become setfable. We get a predicate function, so we can test whether a value is a person or not, and then we get a copy function that allows us to create a copy of a instance of our struct. Now, that is a lot of things to happen just when you create a struct, but there is significantly more that we can do here. So when we define a structure, I'm just going to restart my interpreter because re-evaluating a structure has strange behavior, like the instances are not updated when you re-evaluate a structure. So in the interests of avoiding bugs here, I'm just going to restart my interpreter every time I change the structure. Obviously in production code, you're probably there with your struct design, but as we're doing this iterative approach here, I will just keep restarting my editor because my instances will not be updated and that could cause bugs. Whoops, I've got an unbalanced parentheses. There we go. So I can, on any field in my struct here, give it a, oops, this is obviously the field name. I can give it a default value, and I can use the type keyword argument and tell the structure what type this should be. So I can get rid of this here because that's obviously what it's set to by default. And if I evaluate this, everything would work as it did previously. But if I do this and execute this, we get an error because value of 9 in make person name 9, it's not a string, so we can enforce that the correct types are used on the correct fields. So that's a pretty cool feature. It's not really relevant to what we're doing right now, but it's worth just seeing what happens if you pass in the wrong type. So I'm just going to abort this, it's not necessary. Now if you want to use the default, you can just use the constructor as is with no arguments and it'll be fine. And that really is it for properties. There is one final thing I forgot to mention now, just consulting my notes. I spent 6 hours looking at this last night. We can do this, and if I evaluate this, or rather I restart my interpreter because I've made a change to my underlying structure there, I'll evaluate that structure and try and run this. This should now fail for a different reason, which it does. The function setf common Lisp person name is undefined. It's because we have set this to be read only. So if a property becomes read only, it is not setfable. So if I get rid of this line, and run this again, it works. So that error was triggered because we had chosen to make the field read only, and that prevented the setfable function being created in the background. So when you're dealing with fields, there's 3 extras. You only need a field value, a field name, sorry, but you can give it a default value, you can give it a type, and you can give it a string, and you can have as many fields on a struct as you like. This is the simplest bit of structs, just the fields. The constructor part of the struct itself, and that sounded a wee bit weird to say, gets all manners of interesting. There's like 8 parameters we can pass into a structure here. So we're gonna really have a look at what we can do there. Now the list of things that can be passed into a structure are conc name, constructor, we need to begin to unpack what these things are doing, and probably the easiest place to start, or the most logical place to start, is conc name. So let's get rid of those. And conc name is kind of like the prefix by which we can get at things. So conc name, we provide a prefix. So and again, restarting my interpreter there. So we've evaluated our person struct, but this time with conc name being ones. Now what this does, we do need to comment that out because we have a read-only set on our name field. I'm going to get rid of that read-only just so we can continue to see setf work just the next time I restart my interpreter. But we've got this conc name here, and what that does is it changes the prefix by which we access things. So let's get rid of that. And that, and that. So if we evaluate this now, that did not do what I thought it would do. Let's restart the interpreter. And of course these are examples I all tested last night, and I'm now all worried that they're not working. What I actually have is a syntax error, but it doesn't look like it. There we go. So let's reevaluate that now. And there we go. I do apologise. What we actually need to do is have parentheses around the name of the struct and have the pairings there, the cons list here. So we've got our person name, and then we put conc name here, and if you want to have a prefix, you must remember to have the dash there. If you want the dash, if you omit the dash, you have to omit the dash here. That kind of breaks away common Lisp. The convention. I mean, it'll work, but it'll just break the convention. So if for whatever reason you wanted to change those, I believe the official documentation uses an example like this. So we'll evaluate that now, and so we can get that doctor and dr name. So there's a practical benefit there. We can shorten down the accessor methods if necessary. So that's what conc name does. It just changes the accessor for the fields that we have now. What we can do is we can add to that so we've added this constructor thing here, and we're changing it to make dir, and this works wonderfully well. We can change the function name that is generated for the struct if we want, but there's a little bit more to it than this. You can actually define as many constructors as you want, and so we have this make doctor thing here, or make dir. If we wanted to change the name, for instance, we'd still have to pass in this colon name business. And that works. But what we can actually do is here we now have two different constructors. If we use the make dr, and again I will restart my interpreter there, it's getting slightly annoying. If we evaluate this, we've got everything we want here. Now if we use the make dr constructor, we must continue to use the keyword parameters there, and we can see that we've got John in the bottom left corner. However, if we observe that make doc actually specifies an argument list here, and this maps onto the properties, we can actually drop the keyword arguments, and if I run this now, we still get Fred evaluated here when we look up the dr name with the conc name. So you can have as many constructors as you want. If you provide an argument list, you can just pass values straight in and they will be passed straight into the fields. If you omit the arguments, you will use the keyword. Now, I am curious about something here. This may work, it may not. Now, what I'm actually going to try and do is maintain a struct here that has two properties, and I will have to use various things to set the age. I would expect that age will get its default thing here, and if I pass in a name, that will go to name, and hopefully everything will work. Excellent. So let's change this into a format T. And this will be doctor name, and we'll do doctor age P, and this should be format nil, not format T, of course. There we go. So we get Fred is 24. Now I am curious. Do you know when you spell something so many times it starts looking wrong? There we go. So I'm going to obviously restart my terminal or my interpreter. We evaluate that. That works. So we're going to go with MD. Not sure I know many doctors at 453, but that will do. It works anyway. We can see in the bottom left hand corner that works. So with this constructor, a argument list of nothing will just change the name of the constructor by which we build our struct, but we can create as many constructors as we like that will override or use or change the arguments and bind them to the properties in the structure as we like. So that's and that's what constructors do. There is one other thing. If you set colon constructor to be nil, that will disable the creation of a constructor function. I do not know why you might choose to do that, but that is something that exists in the spec. So we have that. So that's conc name and construct. We're going to look at the copier parameter now, and let's change all of these. There we go. Let's put them all under one another. So what the copier parameter does is it takes one argument, the name of the copy function, and we can use that. So let's go here, let np copy me p format nil. Evaluate this. Oh yeah, of course we have to restart our interpreter. Reevaluate that. And there we go. We're printing out, if we get rid of that line, just so you know there's nothing crazy going on. There we go. We're evaluating that and we're printing out the copy with new person object inside that let. So the copier argument to the def struct, and the value that you give it changes the name of the copier function. And likewise with the constructor, if instead you pass in nil instead of a name here, nil will disable the creation of the copier function. Skipping ahead through my notes a little bit because it is related. We're going to have a look at the predicate function. It behaves basically the same as the copier. And what it enables us to do is just change the name of the predicate function. So if we now evaluate this and run our code, we can get t and nil. So we can see here that the predicate argument to our structs will change the predicate function name, and again, like constructor and like copier, if we pass in nil as the argument predicate instead of a symbol, it will disable the creation of the predicate function altogether. Now, we're going to look at some more stuff here. So what I'm going to do is get rid of all of these because they're not relevant to what we're doing. So we're going to start with a very simple person function, and what we're going to do have a look at the include thing here. And what we can do is we just include the thing here. What's the specialism? Phrenology. I am not a doctor, that is probably spelt wrong, but I believe it's someone who is a specialist in kidney disease, if my memories of house is correct. And we're going to set that type there. And oh gosh, it would help if I could type. Yeah, we'll leave that because obviously it's got a default argument. There we go. So we'll have doctor name, doctor age, and doctor specialism. So let's evaluate that and that. Okay, right. Again with the restarting of the terminal. We can see here that by including our person there, we can get a doctor name function, a doctor age function, and a doctor specialism function. But because this is the start of object orientation, there is a certain inheritance here. You can see here that this still continues to work, because although we have our person struct, we have our doctor struct, the doctor includes the person and is technically, although they're not classes, the closest term I could use is a subclass. It is a descendant of the person struct, and so all of the methods, the reader functions and the setfable versions of those would work on a doctor object, because it does inherit the name and the age from the person, but it does also, by way of including it, create doctor versions of those reader and setfable functions. However, the doctor specialism, being specialism is on a doctor, there would be no person specialism reader function. So this is pretty cool. There's a little bit more to it, of course, and what we can do is this. And again, we'll just restart everything, just so there's nothing left over. We evaluate our person, we evaluate our doctor. If we run this, we see that any doctor that we create includes a person with the age value set as 45. Now, we can use the setfable reader macros to change this later, but by default, all of our doctors will be age 45 for whatever reason. So that's kind of cool, because if we need to set certain things on our structures, I understand that this is a very simple example, but hopefully you can see the implications of that. So that is particularly interesting to me. And of course, if you want, you can set multiple for every one of the fields that exists on, again, for lack of a better term, the parent object. We'll just set that there. You can see that we get John, age 45. But if we specify a value, that will take precedence there. So that is, we've looked at nconc, we've looked at Copier, we've looked at Predicate, we've looked at Constructor, we've looked at Include. We only really have 3 things left now. And a lot of these tend to work together now. These last 3 are interlinked. What we can do is, let's get to the end there. We evaluate that, and then we evaluate this. That is not what I expected. Never mind. We're kind of done with this inheritance stuff for now, so we don't have to worry about that too much. All we really want to do is have a look at this. So we've got our person here. Sorry, just wanted to fix that up. If we run this, oh, I know what I'm doing wrong. I realise I made no attempt to explain what I'm doing. And I had more arguments than I needed. There we go. That works now. Sorry about that little detour there. I got a comment in one of my videos saying it's great when I leave the mistakes in, and that made me so happy. It really did. But what we did here is we have this idea of a type, and we can define how this structure is going to be represented. And with a list, you're saying that although we are creating a person type, that type is basically a list. And this is where the named parameter comes in. So, in a structure that is type list, we can see that the first parameter is the first property, and the second parameter is the second property. But we have no real way to tell. Whether something is a person or not. The predicate function here isn't working. So what we actually have to do and let's reevaluate that struct is we pass in this named argument at the end there, and the predicate function is now working. We can determine whether this object person, this make person P, is a person or not. But technically it's a list, and we don't have any errors here, so our code is clearly executed correctly. So let's actually demystify what's going on there and have a look at that format string. We can see here that when you are using the named keyword with the type, and they work together here, named doesn't do anything unless you have a type, we can see that the first thing in the list that comes back, because we are casting this struct to a list, is the name of the struct, in this case person, and then our second parameter is our first property, and our third item in the list is our second property. And we could also do this with a vector, and I'm just going to return the P object there so that we've got this. Oh yeah, I didn't restart the interpreter. So we can see here that when I evaluate that, we just get a list. The first thing is a symbol representing the person, name, Fred, and 24. And if I restart my interpreter and I reevaluate that, casting to a vector this time, you can see that it's different because we have the hash, but we still have person, Fred, and 24. And that named, when we're using type, because they interact with each other, enables us to use the predicate and the copy functions correctly. So that's what the type and named function do. If there's no type, named is ignored, basically. And if there is a type but no named, you just get a list, or you get a vector without the type, and that disables the predicate functions and whatnot. It's just something to be aware of there. And that really brings us to the initial offset, and that again is related to this type thing that we have here, and then we'll have a little bit of a look at the printing, and then we're done. So we're going to say initial offset 5, and this may surprise you when we run this, or maybe it won't, I don't know actually. You'll notice that here we are creating a vector, and we've got an initial offset of 5. We have 5 leading zeros before we get to the person, the Fred, and the 24. So because we are converting these structs to either vectors or lists, we make no assumptions about the nature of those lists, and if we want to insert the information at some specific point in the list, we can do that by giving it an offset. Maybe we're combining a number of things together, or maybe we're building a more comprehensive list that just happens to contain struct data. You know, I couldn't make any assumptions about that, but if we wanted to, we could do this, and this works for the vector or the list type. We can just use the initial offset there to pad elements at the beginning of the list, and then obviously edit the list or vector coming back and do whatever we want with it. And really that's all there is to initial offset. It's just when we're treating our structures as if they are list-like data rather than structures in their own right. Which finally brings us to printing. Now there's two ways to do this, and honestly the difference is very nuanced. The two options are print function and print object, and you can only use one, you can't use both. And really the only difference between the two is that print function will display nested data to a degree. And I don't necessarily have a practical example of this, but it is something that is available here. So we'll have a look at those and how to work with it. Now there's a few ways we can do this. We could simply say print function with no arguments. If we run this now, make person is undefined, let's actually of course I had this work. Of course I had this working last night, and I was probably up till about 1 in the morning making this work, so it is possible it has slipped my mind. Although, of course, what is equally possible is that I've got all this leftover code and it's not interacting the way it should, or the way I expect it to. So let's evaluate that. There we go. Of course, it was just the leftover interactive stuff here. So what we can do is we built a print function here. A default one, and that displays things with the #s business. This is true no matter which version of these we use. So we still get that #s there at the beginning. Now, print function and print object do not have to receive parameters, but if they do, we can say defun PO, and this takes an object and a stream, and what we can do is say format stream ~a, and we're just going to print out the name, so we'll say person name object, and PF will take an object, a stream, and a depth. And again, I couldn't necessarily get this working the way I thought it should work. It is entirely possible I misunderstood it, but it got... I believe that most of the key things here have been covered. So what we're going to do, print object becomes PO. So we're going to evaluate that, and run this. We'll say, just for clarity, PO. So we've got our PO. We've got our PF there. But it makes no difference evaluating it because I have to restart the interpreter because I changed this, or will change this. and we can see that the print function instead has been called. Now I don't have a particularly nested structure here to demonstrate everything that's going on, but that is in fact kind of a whirlwind tour of structs, all the things that you can do with them, the various arguments, and there are limitations. They are singly inherited, but you can see they create constructors, copy methods, reader functions, seteffable ones, predicate functions. So there's a lot more going on than perhaps you initially thought, and the level of customization and configuration is pretty cool. So please have a bit of a play with that over the coming weeks. I hope it was interesting to you, and we will see you in the next video.